So the first thing I want to remind you of the actual material again. So I'm not going over the concept questions. If you have any questions understanding some of those, please do them. But the first group of the three questions deals with magnetic forces and magnetic torques and dipole moment. Some of this area, I give you a charge particle, and I give you a magnetic field. What is the direction of the force? If you remember, we calculated then what is the force of a wire segment where there's a current I running through the inside of the magnetic field. Then we extended this into a loop and found a general thing that for a general wire loop, a closed loop, the force is zero. We calculated a couple of examples for rectangular, things like that. Then we calculated, however, beyond just the force for a current loop, control the torque inside of homogeneous magnetic field. Questions around that? The second group of three concept questions deals with Leo's law and Bernd's law. There I will give you some, just like in the practice exam, some wire arrangement in a point P, and you should tell me what is the direction of the magnetic field, but really applying basic aspects of Leo's law, ES plus R relative to a certain point P in space. And then Ampere's law, the wire current arrangement relative to a certain closed loop. What can you tell me about the total enclosed current, things like that. And the last group of three problems deals with basic circuits, battery and resistors, the understanding of two resistors in series, two resistors in parallel, what is the total resistors in parallel, what is the total resistor in series, how do you measure a current, how do you measure a voltage over a resistor, a voltage drop, or the current in a circuit. So all of that are not capacitors. So that's not what it is. And then for the three analytical problem, I think it's simply best if we just go through them. So we dealt with similar arrangements like this here, circular sections, and here's yet another example like that. So a current loop shown in the figure below consists of two arc segments with a common center at P. One arc segment has an opening angle of 120 degrees, and the other segment an opening angle of 240 degrees. In fact, the smaller one, the larger one is 120. Two straight line segments join the arc. One arc segment has radius capital R, and the other one capital R over 2. A current I1 flows clockwise in the loop. Later on, if you have not read this problem, it will become clear. It's just simply a choice why I label this R1 and not simply I, because there's a second current appearing later on in the problem, but we come to that. So now determine the magnitude of the magnetic field at point P and the direction of this entire arrangement. Let me just monitor myself here. Starting point, so this is problem 1. So I take this sort of, so to say, together both problems, the magnitude and the direction. So now what we need to really figure out here is how to apply Surrow. The differential element of the magnetic field vector is mu naught over 4 pi, working in vacuum, times the current I1, which I already write in here, ds cross r hat divided by generally, I denote this as little r squared. So this current I1 in both of these sections is exactly identical. So let me re-sketch this here. So here's that point P here. And then, let's see, this is 30 degrees here. You have here then that smallest circular section of 240 degrees. And then this connects to here, this 120 degree section. So this here is R over 2 here, and this here is capital R, the radius. So now the current flows in this direction, so I1 here, and this way here, current I1 here, out here from the smaller inner radius to the outer radius, and then around back here again. So clockwise, clockwise here, okay? So now, when you get a problem like this, I would not right away start with writing complicated stuff down and right away solve it. First, contemplate a little bit what do we actually have here. You have 3 geometrically different sections. Let's label this as 1, 2, 3, and 4 here. So let's start here with 1, I1, with current I1, obviously all 4 sections, the 120 degree segment here, the straight section 4, then the 240 degree section, section 3, and this other straight section 2. And we want to evaluate the magnetic field at point P here. So now let me ask you, for which of these sections do you even have a non-zero magnetic field to begin with?
1 and 3.
Only 1 and 3. So 2 and 4 here have a 0 magnetic field contribution. And let me emphasize something very important here again. ds cross r hat, these 2 vectors, irrespective of where you are on these sections, these 2 vectors are in that plane. And therefore, in general, the cross product of that is either coming out of the plane or going into the plane. It can never be in that plane. Now it happens to be so, well, this is then 0, as you know, if these 2 vectors are parallel or antiparallel. And if you were to look here, ds is going outward. But now, if you take a current element, r hat points always from the current element to the field point where you want to observe the magnetic field. So in this case, technically they're 180 degrees apart. In this case here, ds points inward, that ds vector, in the same direction as r hat, from the current element to point P. So they're parallel, so the angle is 0 degrees. So therefore, as Ben correctly said, 2 and 4 will not contribute. So we only have to therefore worry about 1 and 3. So now let me right away begin the work for this outer section here. Covers an overall angle of 120 degrees. Here, let me write this down like this, 120 degrees. And here for section 3, 240 degrees, as it is written. But obviously, we have to convert this then into radians. So in this case here, 220 would be therefore 2 pi over 3. And therefore here, 2 times of that would be 4 third pi. All right, so now the challenging part, and there you can often make lots of mistakes, is to carefully evaluate that cross product. So let me first read V of Surrow from left to right. Mu naught of 4 pi, the current is all constant given quantities. And if I restrict myself now to section 1 here, then you're moving on a section with a constant distance from each of these little differential current elements to a field point P here. So R here is right away given, little r is simply capital R. It is also a constant, which significantly simplifies this entire problem. You only have to worry about ds cross r hat. So now ds can be now written as, let me write this generally as ds times times a azimuthal angle, azimuthal unit vector, pointing in the direction where you're moving towards. So ds points in the current direction. The direction of the current is inherited to the direction of this ds element, and I'm simply formulating here this vs vector in terms of its magnitude in the unit vector. Since we're dealing here with a problem of a constant radius, you better make use of polar coordinates. Generally speaking, because we have to deal with a third component, of course, strictly speaking, it's actually cylindrical coordinates. So now ds we can formulate here now in how? How can we formulate now ds specifically now for section 1 here? Keeping in mind the fact that r here is capital R is a constant. What is then ds now? Exactly. So simply r times d theta, and we end up with an integral then r over theta. So let me now spin this a little bit further. So we can now evaluate ds cross r hat equals to. So I replace now ds vector as ds, the magnitude is r d theta, so r d theta times theta hat, the unit vector, cross r hat equals to r d theta. So now we have to work out this, this cross product among two unit vectors. And let me, and I think in the problem it was even explicitly given like that, there was a coordinate system drawn. So there is the y-axis here upward, x-axis down, and tell you explicitly that the z-axis is coming out of the plane. So let me denote the direction of k hat like this here, coming out of the plane. So now relative to this positive direction of the k hat unit vector, what type of direction do we now end up here with for this cross product? Can you formulate this in terms of the k unit vector? What is now theta hat cross r hat? Use your right hand rule. Negative k. So take your right hand, point it into the direction of the current here. That's already now ds, or the unit vector of that, of ds, theta hat. Cross r hat, and r hat points from the current element to point P. And therefore my middle finger, as you can see, points into the plane. So indeed, this would be now minus r d theta times k hat. And that's it. And the rest is a little math exercise. That was the most challenging part, I would say. So now let me formulate, therefore, and write this already as an integral. The outer is therefore minus, let me take out all of the constants we want over 4pi. And then we have the current I1 from here. And now we have a bunch of constants in addition to that. We have here not little r, which might vary, but we have a fixed value or capital R. So I have here now 1 over r squared. And then ds cross r hat, I have written this now here. This is minus, I already have the minus sign here. and you have another R, capital R. And then you end up with integral over d theta k hat. And that integral over that theta, I would not go in an exam situation to contemplate. I talked a little bit about this in class, the integration boundaries for this angle. In this case here, it's very simple. You just integrate over an angle. You don't, there is a, you know what this would be technically theta here. So it simply covers that angular region here, the result of this integration here. That's 120 degrees or 2 pi. This is 2/3 pi. And then you can write down now the magnetic field for the outer section. So R cancels out here. You have here 2 pi over 3. So you cancel out 2 and pi against this pi and this 2 here, and end up with a 2 here. And therefore, with a factor 2 times 3 is 6 in the denominator. And the end result is then minus mu naught by 1 over 6r times k. So, and now for the outer section, for the inner section, the inner, we can essentially use the result what we just talked about for the outer section, except we have to now use not r, but r over 2 as the respective radius. So we now have minus mu naught over 4 pi. And then we have an integral. We have the current I1, and we actually take I1. Then we have in the numerator factor r over 2, in the denominator r over 2 squared, and an integral again over d theta times k hat. Let me just spend a minute here just to make very clear that the direction of the magnetic field here is also into the plane. It's just a simple exercise. Take your right hand, fix one point here, any point on that current section. Point your thumb in the direction of the current at that particular point. Your pointing finger points then from that current element to the field point, and then your middle finger points into the plane. So indeed, minus k hat. So now, here, you cancel this out against 1, 2 here. And then the angular region here is then 4 pi over 3. 4 pi over 3. And if you work this out, just quoting the end result here, there's a little bit of math just to combine all of this here. Then you end up here with minus 2 over 3. Mu naught by 1 over r times k hat. And then the end result is, to quote the total magnetic field, is the superposition of both sections. So the inner section plus the outer section. Here you have 1 over 6. You have here 2/3. You multiply this by 2. Then you have here 4 plus 1 is 5. You get something like 5 over 6. So minus 5 over 6 mu naught I1 over r times k. So a problem like this will be on the exam. Yeah.
So when we integrate, does it matter, like, the bounds we integrate from Surrow?
You don't have to worry about it.
Do we have to show like?
No, you can just simply, it's enough if you just simply say, the integral over d theta for that angular section, as you see here, we can write on 120 degrees, which means it's 2/3 pi. This is perfect.
Okay.
Don't get hung up by the integration boundaries to get the correct sign and then overall messing up the sign for the magnetic field, which obviously is 1, 2.
Well, are you going to specify if we can use Cartesian coordinates or cylindrical?
No, not necessarily. I think this is something what you should understand what is best suited to use. I mean, you could have, and I think I've done this in class at times, formulated ds in terms of I and j, and even r hat in terms of I and j. Now you have two vectors with ij cross ij. I mean, it's very messy to work out in the end. Yes, you come to a, but rather use your right hand rule. So let me clear this a little bit here. So now there was one more part to it, which turns out to be, in reality, actually very short. So maybe this one here. So now you have this two sections for which you have a non-zero magnetic field. We calculated that magnetic field at point P. And now you're supposed to do the following. Take this magnetic field as your underlying field and evaluate what is the impact now on a little bar section. So two fixed conducting rails are arranged as shown in the figure below. And a metal bar of length S is placed at the origin. Initially held in place, and the current I2 runs through the rails in a bar clockwise. So this little bar here, this is held in place down here. And now you see this current is going here from right to left here, up here, and then back here. The bar is then released, and you may assume, and this is an important assumption, you may assume that the length of the bar is very short and that the magnetic field you calculate in part A and B is uniform over the length of the bar. So that magnetic field, what you calculated in part A and B, this is the magnetic field concerning the bar. That bar sees that as a uniform magnetic field because that bar is so much smaller than the overall wire arrangement. So you may neglect the magnetic field due to the current through the rails. That's another important element. Obviously, that rail system produces by itself a magnetic field. But you ignore that because, for example, you say, well, the current I2 is extremely small. So now determine the magnitude of the magnetic force acting on the bar the instant it is released, and determine the direction. And that is something which we also have dealt with in class. So, here are my notes. So this was part C. So basically I put part C and D here together now. So generally the force on a wire element with current I is VL of ds cross B. Don't get hung up if one if you use at times C at times DL or DS, it's the same thing. So now we need to evaluate these two vectors. The magnetic field B at point P, you just calculated before in part A and B. So that's a known quantity. And I want to write this as minus B times a unit vector K. So B is just whatever the constants are in that prior problem. And dl is now dl times J. Why? So dl is a tiny little length element in this current section here. So we're evaluating, want to know the force in this little bar here. And the direction is derived from the current direction. So it's pointing upward. So we're in the positive y direction. So that's why I wrote here dl is, vector dl is dl times J. So therefore we're dealing now with dl cross B, that cross product is therefore dl J cross minus B times K. So let me take this minus sign out here. All of the constant, this minus sign out in dl and B, dl and B, and then you end up here with J cross K. So what is J cross K now? J cross K. Positive I, exactly. And now you have here a minus sign. So then it's minus dl times B times unit vector I. So now the magnetic field is a constant. So we evaluated this here now. So you can insert this now back into here. And have then the force F is therefore the current I. The integral of dl cross B turns out to be minus dl B times unit vector I. B is a constant, and you end up simply integrating over dl by itself. So the length of this little rod of length, what is it said in the problem? Length S. So therefore, the end result is then, if you insert the magnetic field from part A and B, this value of 5/6, then you get here minus 5 mu naught, current I1, I2 here. And now I should be a little bit careful here. I apologize, I should have labeled this correctly here as not simply as I, but as current I2 here. So I2 here. That was it, and then I2 here, and then you enter, of course, I1 for generating the magnetic field in this wider arrangement. So then we have minus 5 mu naught I1 I2 times the length of this bar S divided by 6 R times mu naught. So we did quite a few problems like that. In-class problems, we calculated torques. There was a quiz actually on that. The quiz solutions, the quiz problems are always in the files section. If you click on files quiz, I don't know what quiz it was quiz for. The solutions are in there. That quiz is a perfect preparation for that. Please go through that, especially calculating the magnetic torque. So don't start with calculating torque as R plus F, but torque is mu cross the magnetic field. And the magnetic and mu, you should review that, how you evaluate this involving the area of that Y loop. If you would get something like this inside of a given string concept, don't use it. So that quiz is a perfect problem. Any questions about this? Okay, so now let me come to the second problem, the Ampere's law problem. So this looks much more complicated than it really is. So focus your attention entirely on that left sketch for the moment. An infinitely long wire, and the word infinitely should immediately tell you, yes, I can have a perfect symmetrical, symmetrical magnetic field, and I can apply Ampere's law. An infinitely long wire of radius A carries a current density J naught, which is uniform and constant, so there is no radial dependence. That problem with the steps 1, 2, 3, and so on, what I ask you to review in preparation of the quiz tomorrow, has a radial dependence. The current is directed out of the plane, as you can see here, of the figure below. Now, calculate the magnitude and direction of the magnetic field for two radial regions. One time you are inside of that, and another time you are outside of that. So, where is my chalk here? There we go. Part A. So first part was R large or A equals to A, so once you're outside you see the full current. All right, so B, dl or ds equals to mu naught times the enclosed current. And I can tell you, it will be in the exam, not in any way different. The left-hand side for you to evaluate applying Ampere's law will be the easy part. Spend most of the time, be very careful about evaluating the right-hand side, especially if I give you a current density which is not a constant, which depends on R. Okay? So, so here's your wire radius R, A, constant current density, which is coming out of the plane here. And now you're supposed to evaluate the magnetic field outside of that. So you're using an Amperian loop, closed loop, matching to the symmetry of the magnetic field, a circle. So the current is coming out of the plane, the magnetic field, let's say at this particular point, it would be now directed like this, tangent to that circle, and I'm running around now that circle in the same direction here. So a little path element vector ds would be parallel in that particular location to the magnetic field. So now you have an easy time to evaluate this. So this would be simply, we've done this many times, b times 2 pi r equals to, now, mu naught times, well, let's rewrite this now a little bit. The enclosed current generally is the current density vector times the areal vector dA. The current density vector here does not have a radial dependence or any spatial coordinate dependence. It is simply in magnitude a constant, it's J naught times, and let's imagine I call this coordinate coming out of the plane the z direction, the unit vector k direction. So vector j is J naught times k. The areal vector element dA, I write as the magnitude dA, and place this direction using my right hand, defining this relative to this positive direction in the same direction. So therefore you can easily evaluate the product of these two parallel vectors in terms of the product of their magnitudes. So then you have here mu naught J dA. And now we can evaluate this mu naught. J is simply J naught. You can take this in front of the integral and have an integral only over dA. So meaning we're writing down the respective area. And in this case, this is simply mu naught J naught then pi a squared, meaning the area of this circle. So and now you therefore have, let's put this all together, evaluating now, explicitly applying now Ampere's law. So B 2 pi r, P times 2 pi r equals to mu naught, and the enclosed current is now J naught, the current density times the respective pi a squared. And so therefore B has this typical 1 over r radial dependence, which is mu naught J naught a squared divided by 2r. And the pi here cancels out. So that concerns the magnitude. The direction, well, you define relative to, because I have drawn here the magnetic field just at one point. What about this point? What about this point? And so on. So we need an appropriate unit vector. And the vector of r is this magnitude, what I've just written down, times an azimuth over the theta hat, and it's phi hat. Yeah. Any questions about this? I hope this should be hopefully pretty clear. So now, for the inside, so this would be now section A, the second part. This was I, double I, is now, the left-hand side is exactly the same thing. But now we are placing the Amperian loop inside of that. And so now you're evaluating the magnetic field relative to an enclosed current which is not covering the entire area of that wire, but only a subfraction of that. But now there's a deep correlation between the radial dependence of that magnetic field at a distance r and the current relative what you're enclosing by that respective Amperian loop. And that area also goes like relative to the same coordinate dimension in the r, pi r squared. So you will get a very different radial dependency then. So let me abbreviate this a little bit. So this is that B ds equals to mu naught times the enclosed current. Then you have here B 2 pi r. Left hand side we did this before. Mu naught times J dA. All right. Now the current density is a constant. This is given as a J naught. So this would be mu naught J naught times dA. But the area A is not now pi a squared. It's pi r squared. So this will be then mu naught J naught pi little r squared. And now you see here you have the same r on the left-hand side and the right-hand side, which is very different than before. And now you end up with a magnetic field which is proportional to r and not to a 1 over r. So you have then mu naught J naught times r divided by 2. Same direction of the magnetic field, V of r times theta. So in the exam, if you just write down, if I'm asking you quote the magnitude and the direction of the magnetic field, and you would only write this down here like that, that's not a complete solution. I want you to understand, make clear which direction your assumed unit vector theta hat direction is pointing towards. You give a proper description of the characteristic of the magnetic field. So now comes the part where I want you to focus your attention on the right-hand side. Imagine I would give you a wire, which is like the one on the left, where a current density is coming out of your plane of current density J naught, and I give you the same wire, same radius, at a current density, say magnet J naught, but going into the plane. And I would ask you to evaluate the magnetic field inside of that wire and outside of that wire separately. One time current density coming towards you, one time away from you, and then calculate the superposition. You would literally get what you would find if you would not have a wire at all. Laser magnetic field would be entirely cancelled. So the superposition of something positive and something negative in the opposite direction. And here we're using exactly that idea of the superposition of two fields. Namely, the solution to the right-hand side is now the following. You take the magnetic field from the left-hand side that we just calculated, and you superimpose this with the magnetic field for a little tube, not of radius A, but of radius B, at a current density going in the opposite direction. And evaluating the superposition of these two fields at two concrete points, namely at point M and point N. What is the magnetic field for the little bore, for the little core at point M for a current density going into the plane? But out of the plane, but into the plane. So, meaning, let me re-sketch this for a moment. The idea of that superposition of two wires. So you have this, oops, first try this out. This is the problem what we're having here. And you're writing this as the superposition of the following. So here's a current density J naught coming towards you out of the plane. Here's a physical hole here, literally a hole. You're writing this as the superposition of a wire, what you evaluated in the first part here, an entire wire of radius, what was the radius? A, coming out of the plane, plus a wire which now has, well, so that hole has an inner radius of B, the wire has a radius A, so A minus B is this distance here. I call this distance D here. D is A minus B. So at that distance D here, I place now a wire, a assumed wire, and the current density is now going into the same current density J naught. And I evaluate the magnetic field for both of them, and then I superimpose them. And the end result is a magnetic field that I would have of a wire which has a drilled hole like that. So at point, and you're supposed to now evaluate the magnetic field at two extreme points. So at point M here, M and N. So N is really here at the edge, this is N, and M here is meant to be at the center. Let's label this here as field 1 and as field 2. The magnetic field for at point 1 is, and the magnetic field for the wire 2 at point M is now what? So let's first talk about for field 1 here. For field 1 at point M here, so at a distance d here, well, we evaluated that result before. The magnetic field inside of this wire for a radius less than a here. So we have that result, we have that form, we just derived that before. But now we're quoting that result at a specific R value, namely R equals to D. So U naught, J naught, and R is now D, divided by 2 times unit vector J. And the reason why I write here now unit vector J, so I, J, K here, you're supposed to evaluate the magnetic field right here at that particular point and later on this particular point. So you can write here theta hat, the azimuthal unit vector, but since it's at one particular point right here, it coincides with the J hat direction, that's all. Now, what is now the magnetic field for a wire with a uniform current density, which is going into the plane? So take this as a wire here of a radius d, and now you go to the center of that wire. What kind of current do you actually enclose at the center? Do you even enclose a current at the center? No, so therefore the magnetic field is 0. So therefore you have even no contribution here, so no vector. So therefore the superposition of both of them is B of M is simply then the result from the first field only, U naught, J naught, D divided by 2 times unit vector J. So now, so this is at point M. At point N, so B1 of N, what is this now? Well, we also have here an answer. So at point N, it's now the superposition of this field and this field here. So here it would be simply at the edge, and we also calculated here the field for that. So it would be at the radius of A. So here it would be mu naught G naught A divided by 2 times unit vector J. And B2 of N is now what? Well, you're now taking a wire whose current density is going into the plane, and that point is now located at the edge here. That's point N here. But you calculated the magnetic field in magnitude for an arrangement like this already in the first part. We already know the answer to that. So you have to now keep track a little bit of the signs and that radius. So if you compare this to your result from before, but now the magnetic field is going into the plane. The current is not coming out of the plane, the current density is going into the plane. Then you have here minus mu naught J naught B divided by 2 times unit vector J. And therefore, the overall magnetic field B at point N is the superposition of these two here. So if you inspect this here, you end up here with A minus B, and A minus B, I can simply rewrite this distance D here. So the overall field here is mu naught G naught B divided by 2 times unit vector J. So again, think of the problem, if you would have a wire, just like the left-hand side, total current density, wire of radius A coming out of the plane, then I give you a second wire, same geometrical consideration, also of radius A, but the same current density and magnitude, but the direction is going into the plane. And if I now superimpose these two fields, I get zero. What I would have basically with an empty wire, just a shell where there's no current flowing through at all. And that's the underlying idea to solve the problem. Now, the last problem.
Dr. Surrow, how
Yep.
would you do the same problem if the current density was not uniform and then it had radial dependence?
Then you, okay. If that's the case, and that is that in preparation of tomorrow's quiz. So the S mu naught enclosed current. So that would be now mu naught times J dA. Okay. So now let's say J has a radial dependence. Let's say something like alpha times R. Now you have to formulate dA appropriately. Using a polar coordinates in terms of R and A, you can of course integrate all over 2 pi already. Now you cannot take J simply out of the integral. So now it's part of your integration. Okay. Okay, so I will now go over the third problem of the practice exam. That was in fact a Wheatstone bridge. You have the text in front of you, so I don't have to really post this. Let me first sketch the actual circuit diagram. As you were asked in the first part, sketch the above circuit diagram, including your choice of all current directions, along with your choice of loop directions in preparation of applying Kirchhoff's rules. And as you know, I did this yesterday in class. In the review session, it was a chalkboard. It had only one color. So I strongly encourage you to use one color for the actual circuit diagram. For example, red for the current direction, and then for loop direction, use, for example, blue. So I will do exactly the same thing right now. So this here is now problem 3. Okay, so the first part was to sketch the above circuit diagram. So let me just redraw this. Your battery here, and then the junction points are already labeled. You have one resistor here going into a junction B, another resistor here going into a junction D, resistor here just across, this is junction C, and then complete this one with a resistor here going back to junction D here. And then junction D is then overall connected back to the battery here. So this is the overall resistor chain with the battery epsilon here. Let me label the resistors. This is R1, R2, R3, and R4. Okay. Now, let me now draw in here the assumed current directions. All right. So here's your positive pole. So let's take here the current direction here from left to right here. I label this as overall current I here. I label this here current I2 relative to current R2, current I1 relative to resistor R1. Then down here I3, and then here I4. And then one thing which I did not draw into here yet is effectively another resistor, but shown here as a voltmeter, which has a very large internal resistor. And for the moment, I do not want you to assume that you imagine that this resistor is infinitely large and this current is 0 here. So I'm also drawing here explicitly a current IV here. And somebody asked me yesterday about the assumed current direction. It's completely up to you to assume a certain current directions. If you assume the current direction, which is in fact not the proper direction, then you would get a minus sign telling you that the current is actually not flowing like this here from A to B, but for example in the opposite direction. Okay, so now let me now complete the loops. And the loops is really a reflection of the fact that the underlying electrical field is a conservative field relative to charges. So the total loop integral over a closed path is in fact 0. So delta V is 0. So let's choose now various closed loops here. So we start from here clockwise. Again, the direction is completely arbitrary. Second loop here. Then I have one internal loop here going back to the same point, and then one larger outer loop here. So let me label those. This is loop 1 here. This is loop 2 here. This would be loop 3 here. And this would be loop 4 here. Okay, so this is now a little bit more manageable to oversee with different colors. Okay, so now in part B, you were now supposed to translate this diagram into an equation concerning first the junction rule. And the junction rule, let's start with, I want you to clearly label this A, B, C, D, whatever, how many junctions you in fact really have. So let's start here with junction A here, and the way I always do that is current goes into the junction counted positive, current going out of the junction is counted negative, and then the overall sum is equals to 0. So therefore you have here I minus I1 minus I2 equals to 0. Okay? Then we come to junction B here. So you have a current I1 going into that, so that's plus I1. You have current IV leaving that junction, it's minus IV minus I3 equals to 0. Then junction C here, you have two currents going into that, so this is I2 plus IV, and then I4 is leaving minus I4 equals to 0. And last but not least, you have now current I3 going into junction ID plus I4 going into junction ID, and current I is leaving that junction, minus I equals to 0. Let me in fact draw here explicitly here current I here from junction D back to the battery here. So this would be now a complete formulation of the junction rule. So now let's come now to the part where we translate now the loops into respective equations, 1, 2, 3, and 4. All right, so let's do this now. Loop 1 here, and let me just remind you of that. You now have a well-defined direction in which way you walk around here. The current direction is in the opposite direction. Current is from a higher potential to a lower potential. So you walk now from the initial to the final state from a lower to a higher potential. So therefore this is counted as positive, the voltage drop. So this is I1 times R1. Then you go in the current direction, so now the opposite way, you go from higher to lower. Lower is therefore final, higher potential is initial, so therefore it's negative. Minus I2 R2, and then you walk through the internal resistor of the voltmeter. So in the opposite direction, so this would be counted as plus IV RV equals to 0 here. So now let me come to the loop 2 here. So let's start from here with I3 here. So you walk here in the opposite direction, so this would be here now. I3 times R3. Then in the same direction of current IV, so minus IV times RV. And in the same direction for R4, this is minus I4 R4 equals to 0. Then we come to the third loop here. So you walk in the same direction as the current, so this is meant to be, let's first start here with the battery, in fact. Walking through the battery from the lower to the higher potential, so this is therefore positive epsilon plus epsilon. Then in the same direction, so this would be minus I1 R1. And then through the same direction as current I3, so minus I3 R3 equals to 0. And last but not least, the outer loop from the lower to the higher potential, so this is plus epsilon. Then minus I2 R2 minus I2 R2, and then same direction minus I4 R4 equals to 0. So now you have a complete set of formulation of the junction rule and the loop rule, in fact. And you need to practice this. So really spend time on drawing this correctly with one color. In the exam, I would also use different colors that you really oversee that. Blue pen for the loop and a red pen for your current direction, and then apply the junction rule and the loop rule. So now, I would say this is the major part for all of that. And now in the problem, there are 4 parts, D, E, F, and G. While this looks like a lot of text, but this boils down to something actually very simple at the end of the day. So let me read actually part D here. And then we do this on this side of the board here then. So, the voltmeter has an internal resistor which is very large, giving rise to a current IV through the voltmeter which can be neglected. So that current IV here, that current here, I assume now that this is 0 because the internal resistor of the voltmeter is very large. Using this approximation, show that the currents through R1, R3, so R1 and R3, and R2 and R4 are identical, and determine the value in terms of epsilon of known resistors using the results in part B and C. All right, so this is not very complicated. So let me write out now here the junctions, result for junction B and C again here. So B, we had I1 minus IV minus I3 equals to 0. Now with IV being equals to 0, so now the fact that IV is 0, therefore I1 equals to I3. And now for C, we had I2 plus IV minus I4 equals to 0. So now with IV equals to 0, so therefore I2 equals to I4. Okay? So now, with this in mind, we can therefore evaluate now, apply now the equation 3 and 4. So with 3, the result from loop 3, so let me write this out here. So you had now epsilon minus I1 R1 minus, but now I3 is equals to R1. So minus I1 times R3 equals to 0. So therefore I1, this is very simple, is epsilon over R1 plus R3. And in a similar way, you can now, with the same argument for I2, you're using the outer loop, so then you have here epsilon minus I2 R2 minus, but now I4 equals to I2, so I2 times R4 equals to 0, and therefore I2 equals to epsilon divided by the sum, so R2 plus R4. Okay. I hope this is clear. So now determine now the voltage drops over resistor R1 and R2 here as a function of epsilon known resistors. So the voltage drop over here is nothing else than R1 times I1. I already have I1, so I simply multiply this by R1. So this would be now part E. So therefore the voltage drop delta VBA is therefore I1 times R1, I1 times R1, so therefore this is nothing else than R1 times epsilon over R1 plus R2, R3, sorry, R3, and delta V CA, so the voltage drop CA over resistor R2 is therefore I2 times R2, and therefore this is R2 times, and I2 is here, epsilon over the sum of the resistor R2 plus R4. Okay, so now in part F, you were asked, determine the measured voltage across BC, so between B and C, meaning the voltage meter reading the difference between BA and AC. So we are evaluating now delta V BC equals to delta V BA minus delta V CA. So now you just insert this back into here. You already have the result, BC. So you have a common factor epsilon. You can take this out and you can simply write this then as delta VBC equals to. You can take for each of these quantities epsilon out, epsilon, and have then two ratios of resistors, R1 over R1 plus R3 minus where is it? R2 over R2 divided by R2 plus R4. Okay? So, and then the last part was now saying show that for vanishing voltage reading. So now if that voltage reading in that voltmeter is 0, the resistors R1, 2, 3, and 4 have to fulfill the following relations, that R1 over R2 equals to R3 over R4. So you set this whole expression equals to 0. So delta VBC equals to 0. Then what do we have? We have then R1 divided by R1 plus R3 equals to R2 divided by R2 plus R4. R1 over R1 plus R3 equals to R2 divided by R2 plus R4. Simply you set this whole expression equals to 0. And now you can cross multiply that. And then you see here R1 times R2. You have also here a term R1 times R2. And then you have a term R1 times R4, and you have R2 times R3. Those are the only terms surviving, because R1 times R2 you have on the left, and R1 times R2 also on the right. So this cancels out, and what you have left with then is R1 times R4 equals to R2 times R3. And you can exactly write this then as that ratio, that R1 divided by R2 equals to R3 over R4. So therefore, you then have R1 over R2 equals to, so R1 over R2 equals to R3 over R4. So why is this so useful in this whole circuit? It's called, in fact, a Wheatstone bridge. So imagine R1 would be an unknown resistor here. I would not know that. So I can solve this relation in terms of R2, 3, and 4. And imagine 2 and 3 would be fixed resistor values, and I can tune R4. So I change using a changeable variable resistor value, change this in such a way that the voltage reading here comes to 0. And if that's the case, then I can simply multiply the resistor for 2 times R3 divided by that tuned resistor R4 to determine that unknown resistor for R1. That's the beauty of a so-called Wheatstone bridge. So just one more remark about circuit diagrams now that you see the full solution for problem 3 in front of you. Make clear that you redraw your diagram. If you have it given in a problem, we're using one color, then draw your assumed current directions, label correctly the junctions, write in here very clearly your closed loops, a complete set of closed loops, and then first carefully translate this applying the junction rule and the loop rule. That's the absolute key. That's basically the pendant to drawing a free body diagram and then translating this applying second Newton law. And the rest is a little math, a little algebra exercise. There's not much more to that. So I would actually encourage you start first with the 2 resistors in series, 2 resistors in parallel, and then there was another more complex problem with 2 batteries and some resistors to solve for the unknown currents. And if you carefully go through that in this practice problem, then you will be just fine as far as the analytical problem is concerned. All right, so let's stop here.